Hello. I just wanted to take a look at this this worksheet that we had started in class the other day and just keep working through some of these problems with you. And then in class you can ask any questions that you'd like, but I just want you to have some practice with them first. Okay, so we had split them up into different types, and we already looked at the problems that were like 1 through 5. So I'm just going to start down here in the next section, which was 6 through 10. And I would like to look at problems 8 and 10. All right. So we had noted that when we had something that had a variable in it, like 2x plus 1 equals 11, our strategy was to isolate the variable. All right. So that meant subtracting a 1 and then dividing by 2. And then we would solve for the variable, and we commented about how this is where the variable is tied up in our equation. And so what we're going to do is try and get rid of anything else, like in this situation, that would be attached to the x, either through addition, subtraction, multiplication, or division, and move it over to the other side. So we look at this problem and we see, oh, here is something that is attached to this right here. And so I'm going to divide both sides by -2 in order to get the logarithm by itself. So when I do that, I get log base 5 of 7x equals 2 divided by -2 is -1. Once I have that situation, I notice that, hey, I know what logarithm means. This says 5 to what power is 7x, and it's telling us the answer to that is -1. In other words, 5 to the negative first power is 7x. And so I'm going to write that. I'm going to take it out of its logarithmic form and rewrite it in exponential form. So this becomes 5, the base of the logarithm, becomes the base of the exponential, to the negative first power equals 7x. All right, again, when we convert from logs to exponents, or logarithmic form to exponential form, we keep the base, and then these two just flip-flop. So that -1 is the answer in this problem, but it becomes the exponent here. This was the argument in this problem, it becomes the answer. Okay, so we have 5 to the negative first equals 7x. 5 to the negative first is 1/5 equals 7x. All right. Then I'm going to multiply both sides by 1/7. You could also divide by 1/7, but I think it will be visually a little bit easier if you just multiply both sides by 1/7. And we end up getting x equals 1/35. All right, now something that we have not yet talked about in class is that we have to make sure that we are not getting extraneous solutions. For some reason it doesn't tell us to check for it on this worksheet. I don't know why they don't, because it really should say it. And so what we're checking for in these problems, and we'll do some more of these in class on Tuesday, is we want to make sure that we are not taking the log of 0 or a negative number. That just will not work. Let's think about that. Let's suppose we have something like log base 5 of -1 equals 3. No, equals x. All right, and I rewrite that in exponential form. That says 5 to what power gives me -1 as an answer. Right? I don't care what you do to this 5, because again, this power represents multiplication. There is nothing that I can do to a positive 5. I can't multiply it together 3 times. I can't take the square root of it. I can't flip it, whatever, and turn it from a positive into a negative. Right? It just cannot happen. All right, so there's no way that I could take the log of a negative number and have this expression make sense. It just doesn't do that, all right? It won't work. Same thing with 0. If I try to do log base 5 of 0 equals some number, that's saying 5 to what power equals 0. Again, if you think about that, the only way I can have a product of things, which again, this is kind of like a product of things equaling 0, is if there is a 0 included in that product. And this is just a whole bunch of 5s or parts of 5s that are being multiplied together, and there's no way I can get it to be 0. So in these problems, really what we're doing when we check for extraneous solutions is to go back here and say, if I put this 35 or 1/35 in this, will it result in me taking the log of a negative number? And in this case, it's no. All right, so this is not extraneous. This solution is fine. Okay, let's take a look at number 10. So again, just like we said before, in this, our algebra case, we would just move everything to one side to get the variable alone, and here is where our variable is. So we are going to move anything that's outside of that, like this -6, for example, over to the other side. In this case, since it's multiplied, we're going to divide. So we end up with log base 3 of x minus 3 equals 4. All right, now that it's in logarithmic form, I'm sorry, not logarithmic form, now that I have the log by itself and some number on the other side, I'm going to rewrite it in the form that I think we're all a little bit more comfortable with, which is in exponential form. So again, I take the base of the logarithm and I turn it into the base of the exponential function. And then these two flip-flop. So this becomes 3 to the 4th equals x minus 3. All right, so then we solve here. So we say, what is 3 to the 4th? Hopefully you remember that's 81. So we have 81 equals x minus 3. And then I add 3 to both sides, so I get 84. All right, and again, we check for extraneous solutions. We're just looking to see, does this cause us to take the log of 0 or negative numbers? So if I put 84 in here, 84 minus 3 is 81. Nope, that's positive. It's fine. And so this is not extraneous. That is our actual solution. Okay, so there aren't really very many of this type where it's log equal a number. So I'm going to ask you to do 7 and 9 on your own. I just want to point out one thing or two things here. One is this on your worksheet does not have a parentheses around it, and per our discussions in class, if there's anything added after the log that is not in parentheses, then it is not part of what you're taking the log of. I still think that looks a little bit maybe, I don't know, unclear. So I would recommend putting parentheses around just the negative m so that you remember that is the only thing you're taking the log of, right? And so when I am trying to solve, I need to move that 2 over, all right? And then same thing up here. I've got this is my variable, and so I need to move this. In both of the other cases that we just did, 8 and 10, we were dividing to get the log by itself, but when you go to do this, you are going to be adding or subtracting to get the log by itself. Okay, let's take a look at the next page because we are moving into the third type of log problems on this sheet. And this third type, what we call the triangle type, is 2 logs either added together or 2 logs subtracted from each other, and it's set equal to a number. All right, so let's take a look at 15 and 16, and then down here, problem 23. I just want you to look at that one because it's got a natural log in it, and the argument is a little bit more complex here than it is in 15 and 16. So I just want you to feel confident with both of those new situations, a natural log in a problem and something other than just a plain old x or 2 or something like that. All right, so let's go back up to problem 15 first and talk about that. So if we were to ignore the 2 for just a second, you might think, oh, this looks kind of like some of the worksheets that we've been working on where we've been trying to either expand a logarithmic expression or condense it into a single logarithm. And in fact, this one, because of this plus sign, should indicate that, hey, if we're trying to change this in any way, it would be to condense it. It is already expanded right here. We have multiple logs in this equation. So we could condense this into a single log, right? So think for just a minute about how you might do that. All right, hopefully you said, oh, I remember that plus sign means the product rule. And so I can rewrite this sum of logarithms as the log of a product. And that product is going to be x times 8. Again, usually we're saying the first times the second, but it just kind of looks a little bit weird to put the 8 seconds. So I'm just going to write it as log 8x. Right? In doing so, I've changed it to the exact type of problem that we were just doing. Log, a single log equals a number. Right, now one thing that's a little bit different about the last two problems that we just did is we had a base here, whereas we don't have one. That's okay though, because we know what that base is now. Hopefully you're saying, oh yes, it's the common log, it's base 10. So when we go to rewrite in this problem, we just say, hey, no problem, I'm going to do the same thing. Now I've made explicit what was implicit before. And so I'm going to rewrite this with the base of 10. And then I'm just going to flip-flop these two because this is the exponent in the exponential and it equals 8x. Okay. So from here, we would just solve just like we did before. This would be 100 equals 8x. I'm going to come up here. I'm going to divide both sides by 8. So 100 over 8 equals x. The only thing I can simplify here by is by 4. So this would end up being 25 over 2 equals x. And again, I'm going to check to make sure that if I plug it back in, I don't end up taking log of a negative number. So the only place x appears in this equation is the first one. If I put 25 halves in there, log of 25 halves is fine. This is positive, and so I can take the log of it. All right, so let's take a look at number 16 then. Same thing, except now, instead of using the product rule that we did before when we had an addition, now think about what we would use here. Hopefully you said the quotient rule, which would be correct. Right, when we have the difference of two logs, then it just turns into log of a single quotient. So we've got log, again, no base written, so it's implied 10. So then this is going to be x over 2 equals 1. All right, you should rewrite this then as 10 to the first equals x over 2. And then hopefully you see that this just says x equals 20. All right, again, I'm going to just check for extraneous here. If I plug 20 in anywhere I see an x, I just want to make sure that I'm not taking log of a negative number or 0. And so, nope, that is fine. All right, so 20 is our answer. All right, hopefully you're feeling okay so far. Let's go down to number 23. Again, this is the third of the triangle types that I want to look at. All right, again, I don't want you to freak out about those natural logs. They behave exactly the same way as regular logs. Their base is just e. All right, so that's a way that we can get away with not writing a base, but not having any confusion with the common log, which is base 10. So we just have that different notation. All right, so again, just like before, we see the subtraction sign. We should think quotient rule. All right, so we get natural log of 2 over 3x plus 2 equals 1. All right, now this is where things might get a little bit weird for you. Just remind yourself that this is an e right here. Right, but that base, which we don't write in natural log, is an e. So when I go to rewrite it, it says e, the base here becomes the base here, to the first equals 2 over 3x plus 2. Now you have two options at this point. You could turn e to the first into 2.72 like we talked about in class, or you can just solve for x and leave that e in there. I'm going to do the former, I'm going to do the latter. I'm going to solve with e in it because I think that's harder. And so I want you to see that. If you were to just turn this into 2.72, I don't have any doubts that you could do that on your own. So I'm going to do the harder one, and then if you would like to try the easier one on your own, that's fine. So if I'm trying to solve for x, here we would cross multiply. So we would get e times 3x plus 2 equals 2. Again, e is just a number. I realize it looks like a letter, but it's filling in for a number, 2.7-ish. So we're just going to do the same thing that we would if this were 2.7, which is we're going to distribute. All right, so we get 3ex plus 2e equals 2. Right, this is where our variable is, so we were trying to get everything away from that. So we want to get this over to the other side, so 3ex equals 2 minus 2e. And then we also want to get rid of this. This is our coefficient here. We're trying to get this by itself. So we end up with x equals 2 minus 2e over 3e. All right. Now, this is not super helpful in terms of deciding whether this is a legit solution or not. And so you would need at that point to use your calculator to make sure that it is actually not going to turn this into negative, but I promise you it's fine. Okay, last type, and that is the heart type, and we're going to do 2 of those. We're going to do 18 and 20. Right? This type has log plus or minus log equals another log. Right? So hopefully you can think about the fact that this looks a lot like what we just did up here, that our strategy is going to be to condense them. All right, so if we do that, we get log 7x equals log 37. And then this is exactly like the first few problems on the page. When I have log of something equals log of something else, then by the one-to-one property of logarithms, I know that I must be taking log of the same thing. Right? I can't get these two answers the same unless I started with the same x values. So that tells me that x must equal, 7x must equal 37. All right, so once we condense these, it turns back into that really easy type that we liked doing. All right, so then from here, we're just going to solve, divide by 7, divide by 7. We get x equals 37 sevenths. And again, when I check for extraneous, I go to put that back in here. I have no worries. I'm taking the log of something positive, and that is fine. All right, last one. If I've got log base 9 of x plus 6 minus log base 9 of x equals log base 9 of 2. Again, always kind of keep that part in mind, that these all have to be of the same type of log in order for this to work. All right? They should not be tricking you by putting different ones, but it's good to just always notice that they're equal, or the bases are the same. Okay, this is going to be log base 9 of x plus 6 over 6. You really don't need those top parentheses. I don't know why I put them in there. Equals log base 9 of 2. All right, so we have a single expression here equaling a single expression here. So I must have been taking log of the same number. So this is going to be x plus 6 over x equals 2. Again, I'm going to cross multiply, so I get 2x equals x plus 6. I subtract the x and I get x equals 6. And then I just confirm that when I plug it back in, anywhere in here, that it's not taking log of a negative number. So when I put 6 in here, I get 6 plus 6 is 12. 12 is positive, so it's fine. And when I plug it in here, I get 6. 6 is positive, so that is fine. So this is not extraneous. We will look at ones that are extraneous, so I don't want you to think that there are never any that are extraneous. There definitely are, but just not on this sheet. Okay,